we had hit this problem of ultraviolet divergences. And indeed, we see that if we are true scientists working from the bottom up, or at least true Gedanken experimentalists trying to make sense of our world, we've seen these particles, this particle, this spin-half particle psi, and this zero particle phi, and we've tried to study scattering experiments with these guys, and we've managed to figure out the coupling G is there, and we're trying to piece together what theory we have got by doing experiments. We've taken tree-level processes, tree-level calculations, which are certainly the crudest calculations you can do, and we fit to the experiments, and they fit pretty well. But now the next generation of experiments is coming up, and it has high precision, and we know that tree-level just does not cut it, and so we want to go the next step further. This is almost a replay of the actual history of the subject of quantum electrodynamics. And so we try to do loop calculations, and the loop calculations have run into this crisis of ultraviolet divergences. But we see that in a sneaky way, even though we're keeping the energies of our processes at some finite value, we're running our collider at 1 GeV or whatever it is, back in those days, virtual processes, through courtesy of the uncertainty principle, are sensitive to incredibly high energies. In fact, to arbitrarily high energies, right? Because those loop integrals have integrals dq0, if you like, from minus infinity to infinity. Okay? The whole range of virtual energies are allowed. And so we see that that is at the root of these ultraviolet divergences. Okay? And yet, this plugging in the virtual physics is like saying the physics does not change. The basic physics does not change up to arbitrarily high energies. It's just the physics of these guys and this coupling. And it stays the same. And tentatively, we recognize that maybe that's not true. Maybe there's some new physics which is very heavy, so I don't see it on shell, but in virtual processes it comes in, and maybe it cures these ultraviolet divergences. I can be hopeful, okay? Maybe it cancels the worst part of this amplitude, the bad ultraviolet part of the amplitude, and everything works out. And if we want a vision of what that could be, that was given by the Pauli-Villars regulator. It's only a vision, it's a cartoon, it's a toy model, because it doesn't obey the spin statistics theorem. But by God, it is technically simple, because it is just replaying the math that we did incorrectly. But now, when you add everything, you add all the diagrams, the real particles and the Pauli-Villars contributions, before you do the integrals, and then combine these integrands. The integrals now converge, and all the manipulations we made last lecture are rigorously well-defined moves, contour, to rotating contour. All of that is just good stuff. Any pure mathematician would agree. Okay? Except it's a fake. It's a fake of what the new physics up there might look like, as we know. So the first step is we hit the ultraviolet divergences when we start to do loops. The second thing is we regulate it in a kind of suggestive way. It's Pauli-Villars regularization. But that's clearly not satisfactory. And now we want to sort of understand a little bit how sensitive are we to our crazy model of the ultraviolet. The Pauli-Villars particles, which would violate the spin statistics connection. They give finite results, but they are crazy. How sensitive are we truly? I mean, there must be a true story, and this must be the fake story. The true story may be very complicated. Does it matter? Does it matter to the processes we're studying? Let's see. Okay, so let's push on the self-energy calculation. Now that we've done angular integrals, we have a regulated expression. Let's actually try and just calculate it. It is regulated, but so at least we can try and calculate it. Okay? So back to the self-energy. I'll just remind you where we were. We've done these angular integrals, which have brought me these 16 pi squareds. The nice variable was q squared, where q squared is really q Euclidean squared, the polar coordinate, but it's easier to talk about q squared rather than q because everything looks like a simple function of q squared. Okay, that was the easier of the integrals because it didn't involve p in any way. And then there was another term you may remember, and I gather I'm hopelessly wrong in the sign somewhere or another, but this is the Feynman parameter for that Feynman parameterization that simplified the integrals. Of course, these integrals now go from, since they're just polar coordinates, they go to 0 to infinity. And this is the more complicated one because it involves p squared entangled with the q integral. Okay, so let's deal with the hardest integral first. There it is. It's an integral which is of the form, so xi is this q squared. Right? This integral here has this form, clearly. And that's easy. We can just, so I'll just do it. I'll add x and subtract x. Okay? So then this is equal to which is an easy integral, and I can just shift variables from, instead of going from 0 to infinity, I can go from x to infinity and call this c prime. With me? And then the answer is obvious. It's just minus log. So at first we're going to, by the way, I've written it without the regulators because putting in the regulators we're going to just do by hand. This is, you should do it in your head. So right now we've got this thing over here, and there should be a similar one from the Pauli-Villars expression. So there should be, right, in this term, you would subtract the equivalent expression with the Pauli-Villars mass, which I'm calling lambda. So there should be another expression just like this. So naively, you can see the ultraviolet divergence right here. You get log of xi, and you have to evaluate it between infinity and x. And that is not going to, that's the ultraviolet divergence hiding again. But if I had this integral, and then I had another one just like it, like integral from x, where the Pauli-Villars particle mass is showing up, and infinity the xi prime over xi prime, then the infinity parts cancel, and you just get this ratio. Okay? With me? This guy, you would, this one is actually finite, and I'll just write the answer. X, and then it's just over, so there's minus, yeah, there's minus, so it's this. Okay. And you might say, but there should be another term, which is like x Pauli-Villars over c prime squared. And indeed, there, let me see the, x So fine. This is the easy part. Just throw it away. This is slightly non-trivial. Let me write it down. It's equal to log of lambda squared minus p squared x 1 minus x. And then m squared minus p squared x 1 minus x. Okay, and so these are the here, let me put plus regulator, plus Pauli-Villar's terms, just to make this an equation. Just plus Pauli-Villar. Similarly here, let me just put plus Pauli-Villar's. When I say plus, I mean plus or minus, depending on whatever you have to do. Between last week time and this time, I played around with it. So you're staring at this. Now this is a little bit simplifiable, because again, my attitude is we're trying to test this theory that our experiments have seemed to uncover. They've uncovered this particle, and some G, and there's some, you've tested some tree-level processes, and it looks pretty good compared to experiment. And so tentatively, you'd like to believe that this is the theory. And yes, it's possible it's not the theory for all time. I mean, or if you want, for all energies, this is not the theory. Maybe there are new particles with super heavy masses that are there. But we want to test the possibility that the theory is not breaking down here and now. For example, if I'm running at an energy E in my collider, and there is a new particle that's not listed here, let me call it chi. Okay. And the mass of chi is only slightly bigger than E, then this is probably not such a great theory. Okay, it's on the edge of destruction. Okay, so I don't know how to test that, because if this M chi is, if there are 10 species of M chi and they all have weird and wonderful couplings, this is probably not going to fit experiments that well. Okay, so that one I give up on. My best hope, on the other hand, I have the other attitude. There are no new couplings. I'm going to test the hypothesis that there's nothing new out there. But then we're back to these ultraviolet divergences. So let me go for the middle ground, which is this. That whatever new things are out there are much heavier, much bigger than the energies at which I want to play. Okay? Let me see whether I can do any calculation in that way, so that whatever effect these guys have, it's far off shell. And maybe that saves me in terms of predictivity. In fact, it will. Let's see how. Okay? But right now we look like our proxy, our stand-in for the true theory of new physics is lambda. Okay? That's the name I've given to it. So our attitude should be, it is incredibly big compared to whatever energies we're interested in running at. Okay, energies and momenta. That means, back to here, this P is the energy, is the momentum coming through this diagram. For example, maybe we're doing this process, we're calculating the Gress propagator. Why? Because it's something to do with, say, this. It's one contribution to this. Then whatever momenta is coming through here, little p1 and p2 is adding up to this p, and that's what I'm considering. Okay. So this p is some experimental energy, and that's sitting there. And this is much, much, much bigger. Okay? So, in fact, for lambda much, much bigger than p, this is log lambda squared, m squared minus p squared, x 1 minus x. Okay? And the corrections, if you can just do it in your head, are order p squared over lambda squared. Okay? So indeed, if lambda, this is not diverging with lambda. In fact, quite the opposite. This error term is going to 0. So if lambda is 10 orders of magnitude bigger than p, this this is smaller than any experimental error ever seen. Okay? So this is the guy. This, however, looks very sensitive to lambda. It looks like unless I tell you what lambda is, I'm not going to be able to predict anything. That's an incorrect conclusion, but so it appears at the moment. Okay? So let's keep that dangerous guy. Okay, so that's that term.
Can I ask something now?
Yep.
So we have recrotated the Q guys, but the P guys are still...
The P guys are just what they were. It's fixed, whatever experiment has given us.
But this is a 4 momentum P squared, so E
It's a
squared
4 momentum
minus...
P squared. Yes.
So when you say lambda much more than P,
It could be much, in general, lambda would be much bigger than P mu in some rest frame of the lab, right? Basically, it's an energy, or if you like, some center of mass energies that you have access to. It's bigger than, so you can always phrase it in terms of Lorentz invariance. So in this case, P squared. So that P squared, the way I drew the diagram just now, that would have been the center, that would be in the Mandelstam S, basically the center of mass of some colliding story. And we're saying that this is, you say, well, why don't I produce the truth, why don't I produce this new physics, which has mass lambda? And that's because the center of mass energy squared is so much smaller than lambda, okay? But this is absolute, it's crucial, if you watch every move I made, that I in no way analytically continued P. P was not the thing I'm integrating. I was doing an integral over Q, and I rotated the Q axis inside a contour integral. That was all I did, and turned it into a kind of 4-dimensional Euclidean integral for convenience. Okay. Yeah.
In your diagram, is the momentum P the momentum of a virtual particle?
It is the momentum of a virtual particle. However, that's why I say, why would we, for just as an example, why would we be considering this diagram in the first place? And so, one possibility, but we can think about this, is, so let me give you two answers. Okay? One is, which will be related to your homework, is, for example, this P, it's off-shell, because I have some source that can make that. So off-shell means it only is traversing a finite extent in space-time. Okay, it can't go arbitrarily far. Well, that's okay, because I have a gun called particle creation of this guy, and a detector called splitting it apart. Okay. But in that case, this P is, even though it's off-shell, it is an experimental energy, right? If time is going this way, P squared is what you call Mandelstam S. It's the center of mass. This is P1 and P2. P squared is the center of mass energy squared of this process. Okay. Now there's another reason that we might be interested in fact we are interested, is because we'd like to get this dressed propagator because it's the pole in the dressed propagator that corresponds to the physical mass, as we discussed some lectures ago. The mass parameter that you're seeing here is just some crude approximation to the physical mass. It's the propagator and the true dressed propagator, the pole in that, which we'll return to study in a little bit. That is the physical mass. And so this P is roughly, in that calculation, the P would be taken to be roughly the physical mass of this scalar particle. So again, it's a very experimental, if I'm able to produce this guy, it's some very experimental energy, right? Namely, P squared is the mass of the particle. So in both cases, these are very finite P's, and I'm taking, however, some new physics scale, represented by these Pauli Large particles, to be much higher than those experimental energies. Okay, so in particular, it's much larger than the physical mass of this particle, or it's much bigger than some other energies that I might use in some off-shell process. I might use this as an off-shell process. If time goes this way, it's again some other off-shell process. P squared is then what we call immense and t parameter. Again, some experimental thing you can relate to the scattering angle and the center of mass energy. And so, indeed, p is always, in this process, is always some experimental. It's not maybe the most obvious experiment. This is not an obvious parameter. You have to learn it. But you know that basically S and T and U and all these things are related to all the scattering angles and the energy of the collision. Okay. So where was I? Oh yeah, I was doing this other part of the integral, the easier integral. Let me do that. Integral. So that is an integral of the form dc c over c plus m squared. And that's easy. That's even easier. Just do this. And then this is equal to the integral dc of 1. Is that. And then minus this m squared over c plus m squared. Okay. And that's it. So again, there are some Pauli Villars contributions, and you need more than one Pauli Villars field, basically. But basically, the job of these things see, if there's cancellations, this thing doesn't depend on m. Okay? So when you compare it with all the Pauli Villars things, the net result is to just throw it away. It'll cancel with all these guys. Okay? This guy, there will be something that looks in net like so. Okay, so the effect of the Pauli Villars will be something like this. Actually, if you do it honestly and use 3 Pauli Villars fields and so on and so on, it'll be some linear superposition, a linear combination of the different types of lambda. I'll let you do that yourself, but this is the kind of expression. And then this is, and again, you're getting these sort of logarithmic, sorry, wait, I screwed up. I already screwed up. Yes, the resulting calculation. Okay, to be finite, so I actually said it right, but then I had to be. So you're going to have some, you'll have terms that look like this, okay? And but there'll be different sort of. There's now several Pauli Villars fields, and you can choose these coefficients. Well, here I'll do it plus or minus, which you can choose the statistics for each particle. The main thing is that this is logarithmically divergent, and no, it's not. It's linearly divergent in C, which is quadratically divergent. So it has to cancel against some linear. So this integrand behaves like 1 for large C. That's what I'm saying. This integrand looks like it also behaves like 1. Okay. But I need to choose the
Wait, why does m squared over c plus m squared behave like 1 as c goes to infinity?
yes, sorry, that was the one I already did.
Oh, that one.
No, sorry, I screwed up. That's the one. I'm done with it. This behaves like log.
Right, okay.
Good. So let me just see. So I get m squared here. Here, let me do this in my head. I'll get these lambda I squareds log So, if lambda, the sum over I plus or minus if this is equal to m squared, okay, so I have a bunch of heavy particles with oscillating statistics, but so let's say that 3 lambda 1 squared plus lambda 2 squared plus lambda 3 squared, and let me choose the statistics to be, you know, minus plus minus or something. If this is equal to m squared, okay, that's all I'm saying, then did I do it right? Then the log divergence is not present. Yes, for very large lambda, for very large C, where we're testing for the log divergence, we could drop this. And if I choose my Pauli Villars fields to have these kind of masses and statistics, then you see I would actually not get a log divergence. But then you'd be left with some finite thing, and that would look like this, minus let me erase this in favor of this thing, that. So, regulator diagrams will look similar to this, but with oscillating statistics and with different masses. If these masses are carefully contrived to have this feature, then the true ultraviolet divergence, where you just get infinity, we don't know what we're talking about, even mathematically, that is no longer present. But then you can still do these integrals and get a finite answer, and it looks like this, where this is some linear combination of the lambda squared I. This is also a linear combination, but it cancels to an incredible degree by contrivance. When you check this, it'll be something which is actually order lambda squared. So you can get combinations to cancel to this degree, but then the combination that shows up here, you can do it yourself as an exercise. Is order lambda squared. I should just, while I'm at it here, let me do this guy. This guy is a 1. Okay, so if you want, let me not cancel it just yet. Let me show you blow by blow what happened. So there are 3 Pauli Villars fields. Each of them has a 1 type contribution, but one of them is a -1 because it's the opposite statistics. Let's say this guy. And then the next one is a +1 because it's got the same sign statistics. And the next one is a -1. That's why I actually had to choose 3. Okay. So with 3 Pauli Villars fields, the 1s all cancel out. Then we're down to, so the quadratic divergences cancel by choosing these 3 Pauli Villars fields with different statistics. The log divergences cancel because I chose this relationship. I chose very arbitrarily just to get finite results. And then whatever was left is written here. And we wonder whether experiments are going to care about my choices or not. Okay, that's the hanging question. But at least the math is okay, so we now have these regulated answers, and so let's see what the physics is, and let's see whether this matters or doesn't matter. It surely matters in that at least now I'm looking at a finite expression, but it seems such an arbitrarily chosen finite expression that I have to ask whether it's physically meaningful. Okay, that's the only question. So let's just do that right now. I don't want to hold any sense that we are completely crazy here. So let's just see what happens. So let's calculate what was all this in aid of. It was to calculate this thing. The dressed propagator. This is the dressed propagator. This is why we spent all this time, just to calculate this one thing. Okay? The dressed propagator. Let's just plug in what we've got here. It's equal to I on top, p squared minus m squared. And then let's plug in that the easier answer, that thing over there, which is minus g squared m squared over 4 pi squared log lambda squared okay. Where did this term come from? It just taking this piece here of sigma with this evaluation, plugging it in. Okay. So, but it keeps going. Then there's the plus 4m squared minus p squared over 8 pi squared g squared. And then this thing has to be plugged in. It's going to matter later, it doesn't matter right now, but if somebody was keeping track of I epsilons at every step, you'll remember that the propagator, wherever m squared appeared, it was really the propagator, m squared appeared in a propagator that went minus m squared plus I epsilon. P squared minus, q squared minus m squared plus I epsilon. So wherever you see m squared, you can put the I epsilon back. We dropped it for convenience in writing all these things out. To say, wherever you see capital M squared, there should have been an m squared minus I epsilon. So I'll put it in there. It's just for completeness. It doesn't matter for what we're doing right now, but it's going to matter for what we're going to do just next. Okay. So, so this is it, right? And we're not yet. It looks bad because it looks like, yep, if this is something. It's some little Lego block of a physical calculation. It depends on this regularization issue, and this regularization issue looks totally arbitrary, and it seems to make a huge difference to the answer. Look, it's not insensitive. You want insensitive? This is insensitive. In fact, just throw it away. I'm throwing it away. This is horribly sensitive. But with just one line, yes?
So just to reduce the confusion later, the second m squared must be little m squared. Those are masses of scalar field, and the other things are scalar.
Wait a second.
The second m squares must be p minus m squares, those m squares. No, in the starting point. So in the denominator,
oh,
yeah, all
thank
those
you,
are.
thank you, yes.
Contribute.
Crucial.
Yeah.
Yes. Little m is my symbol for the scalar. Okay. These capital M's have shown up because this is all the guts of these loopy diagrams which evolved from you. So this is correct. Thanks. Did I screw up anywhere else? No, it never came up. So this is good. So yes. Now I'll make it all go away. All your problems will be solved. And this is it. This is what I'm showing you is what normalization means in just the simplest case study, and it never changes. It just gets more complicated, but it never changes the thing. And And that is that we can rewrite this expression as 1 minus g squared okay. What I've gathered here are what I've gathered here are all the terms that go like p squared, that's all. Okay, just plugged it in here. But I'm actually going to pull this factor out of everything. Whatever was the coefficient of p squared, I'm pulling it out. Everything else, I'm factorizing everything else by pulling out this factor, which means that I'm going to get minus little m squared plus little m, so pieces that look like constants. Oh, here. G plus g squared just to say, if you do this exercise, when I wrote this, I don't mean literally log. When I say log lambda squared, lambda, I'm not telling you whether it's this, this, or this. You'll just see it's some, what I'll call a dumb linear combination of the lambda i's. Why dumb? Because there's no specific cancellations that are happening. So it's just order. If these things are all of the same order of magnitude, then it's going to be that order of magnitude. Whereas this is not a dumb linear combination, meaning it's a highly contrived linear combination, which I've chosen to cancel. Okay, so that's all I mean by this expression here. So I've written that, but you see, this is incorrect as written. I have to divide by this. So this and this cancel and just give me these terms that are independent of p squared. Okay. And then finally there's the one which is truly a weird dependence on p squared. So I'm going to write that term down.
Isn't there a p square dependence also from the x integral? It has a p square.
I mean, just doing this, there's p
Because there's a p square in the factor in front, right? 4m square minus p square.
Yes. Let me tell you what I'm up to in a second.
Just to point out the errors I pointed out last time.
Yes.
Actually, if you did correctly, you don't have any 4m square terms in the second big terms. So in the second
Really? How
third,
could they?
so
It's all the way back at the beginning.
yeah.
What's that?
So you just made one little mistake
And
at the
things
beginning,
added instead of
and
canceling.
then it propagated so far. So if you did everything correctly, you will not have 4m square terms over there. And that is true because if you have non-trivial function of p in logarithmic divergence, you have some trouble.
Yeah, that would be
So,
terrible.
yeah.
So you're
Yeah.
saying that term's not?
Yeah.
Really? And last time I just didn't.
It was 2 lectures
I
ago.
think we agree with that.
We agreed on it last time, did we? Okay.
Well, I checked with him. I got
Oh,
the same. I got the same thing he got.
Yeah.
Okay.
That's what I'm saying.
And so there was just some step where I had two terms that should have canceled.
So in
And
some
Yeah.
step, you need to minus or plus them. You just made 1 plus minus
You
error, and
added
then
4m instead of subtracting it, so you ended up with 8m instead of 0.
zero.
Yeah.
That's what I wanted.
Yeah.
Okay. So I'm willing to trust you on it.
yeah.
So that's right. yes, let me finish writing the expression and then you'll see the sanity of the way I've decomposed it. Basically, I'm taking this expression, it looks bad, and I'm writing it in a way which is meant to make it seem less bad. And, but the way I'm doing it is ever so slightly non-trivial. But let me actually write it down. Plus e squared over 8 pi squared g squared integral dx.
So this is just a pure random function of it.
And log of okay, now let's check first, before making sense of this, let's merely check that it is actually the same thing as the line above. Okay, that's all I want to do for a moment. This 1 is there, okay, that's that guy. Where did this term come from? Okay, there's the p squared, but it looks like it's p squared times some function of log p squared here. But actually, this log, I can write it, I can split the log, I can write it like log of lambda squared over m squared, minus log, plus log of m squared over okay, obviously this m and this m will cancel and I can put it back here. Okay, so I can definitely do that. So then there's a piece which is just p squared times a constant. That's what I pulled out here. So there, this term, right? So this 1 is matching this guy. This term is matching that guy. These two terms are matching that guy and that guy. The fact that I divided by the same thing I multiplied by should make everybody happy. Okay. And then there's this term, okay, which is just this guy. Okay. This log with this integral and this thing is this guy. You might say, wait, this term here, which part goes all the way back here, this term here had an integral that had to be done in x. But since it's independent of x, I did that integral in my head, and there it is. Okay, so so it looks like the same thing. Okay. Now, why are we writing it like that? Well, for these reasons. One, it looks like this whole thing, this factor here, I can think of it as a kind of a 1 over z. You see, if I call this factor 1 over z, then I can erase it and just put a z here. Now, we already discussed what a z like this means. If everything else looked like p squared minus m squared, an extra z here would really be saying that while I thought I had a gun and a detector where the amplitude to emit the particle and absorb it, let's say, okay, this is what I was expecting. if somebody says this, that doesn't bother me. It just says that the efficiency of my gun is really root z rather than 1. Okay? The reason it looks like this is because we choose, we say that I am considering at source j. So in fact, the real here, maybe I should have said like this. In this little game of catch we're playing, the amplitude is equal to integral d4x, integral d4y, integral d4p, integral j of p I over p squared minus m squared plus I epsilon j. If somebody says, no, I feel like using this propagator instead, then I would say, look, that's not, you're not doing something very physical. All you're doing is telling me that your j is equal to my j times root z or something. See that? That this is a kind of a convention that we all have. It's almost really telling you what I mean by a unit source. Now, that is the deep meaning of that factor, that it is secretly something that is mere convention, whether I have this factor or I just say, throw it away, just throw it away. Okay? It's mere convention. And indeed, the formal way, so that's the meaning of it in terms of the strength of a source, but the formal way where you don't have to think about Gedanken experiments and all of that, just follow the math, is simply to say that, so the formal way is if you have t Fourier transform, okay, let's do it fast. If somebody gave you this, and you said, it's pure convention, all this nonsense about z, I would say, yeah, here's the quick way to see it. I will define a new field, phi nu, which is equal to your phi over root z, in which case, so this is just a change of your variables. It's like when you do a change of phase space variables in some canonical transformation in dynamics. It's not changing this. It's just changing your coordinatization of the physics. It's not changing the physics. Similarly here, if you do that, then this thing will of course just come out to look very canonical. Okay? Now, once you appreciate that it's pure convention, the rule is quick. Just throw away the z, please. That's it. Okay? Then we're done. But the deeper point is simply because it's convention. So we recognize this factor. If everything else here in the braces just looked this simple, then we would know that this was pure convention and we'd be done. Unfortunately, the thing in the braces looks like this mess. Okay? Now, how messy is it? Let's just pretend this term didn't exist with the log p squared. I don't want to see it. Let's just drop it. Actually, it does look about as simple as this thing. Because here is this factor, this sort of z factor, so-called wave function or normalization factor. Wave function or normalization, they call it because of this. If you think of this field as a kind of a wave function in the sense of, if you ever learn field theory in terms of second quantization, then, but really we should just call it field renormalization. That's the correct word. But a traditional word for people who thought about field theory a little differently is wave function normalization. And that's accomplished here. So we're always at liberty to do this field redefinition or wave function normalization. But this term here is a constant, meaning it's made out of coupling constants and masses, which is to say a bunch of constants. Nothing dynamical, no kinematic information, no p-squareds, no nothing. It's just some constant number. So indeed, if this term was not here, you'd have something that had a z and then a p-squared minus something new. Well, let's give it a name. Okay, here. I'll just define it to be m squared, little m squared, renormalized. I don't know if the camera picks it up. Anyway, there it is, m squared renormalized. Why? It's playing the role that if I were just doing tree level diagrams was played by m squared. Okay, there. In fact, if I just drop all the loopy stuff, it is just m squared. So I'm just, because it's again just sitting in this propagator with exactly the same momentum dependence or independence as m squared, I'm just giving it this name m squared normalized. So far, how do things look? What's the scorecard? So our propagator is equal to something that has this form. And was it supposed to? So let me see. There was a minus should have stayed, right? Okay, so this is what we are now staring at. And this is not meant to yell out lots of physics at you, not yet. But it is meant to yell out one thing at you. There is no sign of the cutoff dependence.
Should there be a z in that term somewhere?
Yes, sorry, absolutely. So this one shouldn't have it, of course, right?
Right.
Because I've defined that just to be m squared. But this one should have had it. Okay. So let me put it back. That's important. So I have to temporarily retract my claim. And his grade will reflect that. Okay. So we're staring at this. So well, it looks well. I was hoping to claim there's no lambda dependence left. Okay, whatever else this might mean, but unfortunately there is some lambda dependence left. Okay. However, I'm going to write it like this: plus I'm now going to erase it. If you imagine, so let's just work in all we're doing is perturbation theory in 1 over the propagator, remember? So that's why we're calculating self-energy, because 1 over the propagator is the right way to think, okay, from that earlier discussion. Well, if I do perturbation theory, you see that, in fact, expanding this 1 over 1 minus g squared term, you get a, I could just as well erase it and put 1 plus g squared. Okay. So here, put that, 1 plus g squared. Okay. I have no way to distinguish the original expression from this expression to the order and perturbation theory I'm working. Right? It looks like this. And even this term is order g to the 4th. Okay? So in fact, let me get rid of that and just say plus order g to the 4th. Now you might say, you're cheating. In that g to the 4th is cutoff dependence. Okay? I mean, so far. So right now I'm going, ta-da! See, there's no explicit cutoff dependence. There's no explicit cutoff. Of course, it's hiding in the definition of this and this. We'll come to that in a second. But at least it looks like it's gone temporarily. But even there, you would disagree with me. You'd say, no, you see that g to the 4th term, if you bothered to write it out, there'd be some cutoff dependence explicitly there. You haven't got rid of that. It's just decided not to write it. And I'd say, look, I only computed to order g squared in self-energy. If I computed other terms of order g to the 4th, who knows what would happen? Maybe that would cancel. How can I just keep ad hoc something of order g to the 4th when I'm not calculating everything to order g to the 4th? So don't prejudge it. So I'm saying all I can do, since eventually we're going to, believe it or not, we are going to conquer all of perturbation theory and normalization. But all I'm doing is a case study at this order. So leave me alone. Okay, so that's it. That's all you're getting to look at. We are not allowed to question that term. So now we have to ask, are we supposed to be happy that this is at least finite? Or in fact not, because in fact we know that z is secretly this, and we know that this is secretly this nightmare expression here. Okay? And I say we're supposed to be happy, and for a simple enough reason. First, I'm truly imagining for the moment, meaning for a month, I'm truly imagining that there really is new physics. And this is some proxy for that new physics, and there's really some finite value of z. The finite value of z that you get from doing this, the true physics, the true heavy physics at scale lambda, might not look exactly like this formula.